Welcome along, ladies and gentlemen, to your weekly seminars from the SETI Institute. Today we're doing things a little bit differently, as you can tell. We've got a special panel to discuss the latest results of the LCROSS mission. We're joined by the PI, Tony Colaprete. Tony did his graduate and undergraduate work at University of Colorado in Boulder. He has that in common with the second member of our panel, Dr. Jennifer Heldmann. She did her undergraduate at Colgate University and her graduate work at CU Boulder. And Diane Wooden, on the end, did her undergraduate work at UC Santa Cruz and then graduate work at Stanford and at UC Santa Cruz again. They're going to talk to us today about the latest results of the mission that they've been involved in, which you are all no doubt familiar with. And we'll start off, each of the speakers will be speaking for about 5 to 10 minutes, and afterwards we will then open the floor for questions. So if you have any questions that you think of, lock them away in your brain and give them to us after the talk. So we're going to start out with Tony, and Tony, you were the PI on the LCROSS mission, so can you maybe take us from the start of the conception of the LCROSS mission and walk us through how it was chosen and what it was designed to do?
Sure, yeah, and I kind of surprised Adrian with not having any slides. Later you're going to see why. I'm actually going to just use a tool where we can walk through the LCROSS data kind of as we saw it real time and tell the story that way. But as a background, LCROSS was a mission of opportunity about 3 years ago that was realized when LRO had to move to a larger rocket from a Delta II to an Atlas or Delta IV. At the time we didn't know which it was going to do, or which rocket it was going to move to. But in the process of moving, it was such a big jump, they essentially gained or had an excess of about 1,000 kilograms that could go to the moon. So NASA put out a call saying, what can you do with 1,000 kilograms going to the moon? And by the way, we need to know in 3 months. And it was a very realistic. LRO had a launch date, and this at this point was about 2.5 years before that launch date. And so everything had to move very quickly. So there was, I think, about 19 proposals that were submitted from all over. I think NASA Ames put in 6 or 7. We really wanted to win this. We put in actually 3 different impactor concepts, amongst others, orbiters, landers, and everything else. In the down select process, there were 2 impactors in the final 4. Ours and LCROSS and concept from JPL, and then an orbiter and a hopper. And then in the final selection process, LCROSS was selected. And LCROSS, so one of the principal differences between the LCROSS impact concept and all the other impact concepts that were there was what we called the shepherding spacecraft. We weren't the only ones to cheat the system, but we, I think, cheated it in the smartest way. There was 1,000 kilograms to the moon, but so any impactor mission, or you had to live within that, and to make an impact you need either velocity or mass, and you like to have both. Because of celestial mechanics, you can really only get your velocity so high to impact one of the poles. So we said if we put all of our mass into the impactor, into the spacecraft at 1,000 kilograms, you can only have maybe 1,000 kilogram. And it's not that, because you need some fuel to get there. So in the end, it's only maybe 600 or 700 kilograms of impactor. And then you rely on LRO and other assets to observe entirely. What we decided was, well, why don't we use the spent upper stage of the rocket? And eventually the Atlas V was selected, and that upper stage is the Centaur. It's about 2,300 kilograms empty. So it's a much more massive object than we could have fit into 1,000 kilograms. So in a way, we got about 3,300 kilograms out of the deal. And we weren't the only ones to think of this. Langley actually put in a concept similar to this. but again, the JPL's impact concept, from my understanding, just had impactors that fit within that 1,000 kilograms. And they relied also on LRO and other assets to observe. What set us, LCROSS, apart from all those was this shepherding spacecraft. And this was actually, in part, a concept proposed by Northrop Grumman, and then we worked with Northrop Grumman. I think that's roughly. The shepherding spacecraft not only towed the Centaur and targeted the Centaur, but it followed the Centaur in. It had a suite of 9 instruments on board. And those 9 instruments had a very unique view of the impact, looking straight down. And as you'll hear, I think in a minute, that was very, very advantageous. Let's see if I can fix this. Try on this side. And so that was key, and that is, I think, eventually what led to the selection of LCROSS over all the other impactor concepts out there. No other, we did not rely on LRO or any even ground-based observations necessarily to make observations. We were bringing our own suite of instruments along. So that was about 2.5 years ago, and I remember our first science meeting. It was about the proposals went in around December of 2005. The selection was in about April of 2006, and we had our first science team meeting of May 2006, and we changed the entire payload pretty much at that meeting from what was proposed, which is always what you have to do when you start these things. And it really, well, that demonstrated, you know, that the fact that you were in such a short schedule to propose something, you wanted to rethink it and be more clever, and you get smarter just in that short amount of time. So we did that, and then we were off and running. The payload was developed at Ames. We delivered it in about 15 months, integrated on the spacecraft in about 18 months from the time we were turned on. And that included all 9 instruments, an entire spacecraft panel, everything. So we demonstrated a real fast-paced concept mission. The instruments we used were, a lot of them were off-the-shelf parts, off-the-shelf instruments. The spectrometers came from, for example, Ocean Optics. Many of you are probably familiar with them. The near-infrared spectrometers came from a company called Polychromics. Their instruments are used primarily in handheld carpet recycling scanning processes. And that was key. Right after we were selected, I got calls from a variety of more typical, I won't name names, typical industries who provide spacecraft instrumentation or space instrumentation. And when they heard our budget and our schedule, they kind of said, thanks, goodbye. And but then when I talked to these other companies who were in industry, who were in commercial business, I told them our budget and our schedule, and I said, wow, I want to put you on a firm fixed price contract, again, something unheard of in the other space industries, and I need a engineering unit in 9 months. I need a flight unit, and they asked me, why so long? and that was really key. And one of my favorite quotes was from one of the CEOs of one of these companies. These companies, Polychromics, every one in their companies signed the inside box of their spectrometers, and they're now on the moon. And there was all 9 of them. You know, small companies. They said, we make money selling units. We don't make money developing units. And that's very different than a typical space instrument. Is where the money is developing. You know, you take 5 years to do PowerPoints and then build it and whatnot. And sometimes that's necessary. We worked definitely within the capabilities of existing hardware, and that's what allowed us to do that. Is the science team was very good in saying, we don't need absolutely this requirement. What is good enough? And that was the mantra I pounded into the science team and the payload team consistently, is we need to do what's good enough. Not better, but good enough. And what that allowed you to do was meet in the middle and find materials and hardware and instrumentation that was good enough, but allowed this rapid development and flying. And I'm glad to say that the same approach was taken on the spacecraft. Northrop Grumman, you know, they build billion-dollar things, not $79 million things. The entire project from start to our closeout is $79 million, and we're under that cap now still. We're under budget, and we're way ahead of schedule. The spacecraft sat for about 3 or 4 months kind of in mothballs while we waited for our ride. Northrop Grumman had to go and really redefine how they did business. They went to their advanced concepts and treated this as an experimental spacecraft within their broader and corporate, definitions. That allowed them the latitude to work in this kind of fast approach, this what NASA calls Class D environment. And they were incredibly successful at doing it. We used a TDRS tank, an old TDRS tank, stole that from someplace, and we used LRO avionics. This was a fantastic cooperative story, actually, between LRO and LCROSS. At first, LRO was like, "You're doing what? You're sticking somebody between us and the rocket, and they have only 2 years to build it," But in the end, it was we caught up with LRO, and we were using the same avionics, the same command and data, computers, batteries, and power source and whatnot, comm system as they were, and that was to one. We just took essentially the second off the line in the assembly line. But what that did is once we caught up with them, we were essentially doing testing in parallel. And we would find a problem, tell them, they would find a problem, tell us. And so essentially it was this mutual effort that brought us both to the finish line in I think an incredibly a model way for other NASA projects going forward. So that got us essentially to a launch in June 18th of this last year. And the concept is basically to excavate material from a permanently shadowed crater at the poles of the moon to look at the source. Our primary mission goal from ESMD, we're an Exploration Systems Directorate mission, not a science mission directorate. We needed to understand the form and quantity of the hydrogen as a potential resource for future missions. And so that was our direction. Now, you can't really do that without accidentally doing science along the way, luckily. So we are happy to say we're doing science to answer that question. But that was our primary goal. So the point was to excavate dirt, to lift it out of the shadows into sunlight, and so we can actually see what's inside one of these craters. And we were first targeting the South Pole, and then the launch moved, and then we were targeting the North Pole, because the moon, the celestial mechanics don't stop, and we required sunlight and particular angles of view and whatnot. And then eventually we went back to the South Pole. Things got moved out enough for us, so we went back to the South Pole. That said, we had to limit our area of targeting, not just to anywhere in the South Pole, but to a specific area that was determined primarily by illumination. Where was the sun at the time we were going to impact? What was the angle to Earth assets? What was the angle to LRO even, and these kinds of things. And that ultimately constrained our target area to a place on the moon that you'll see called the Cabeus region. The Cabeus region is really centered around a large, very degraded crater called Cabeus or Cabeus. And then it has a number of outlier craters, Cabeus B, Cabeus A, and whatnot. And those were the craters we were really interested in. In the end, we selected Cabeus primarily because of its inherent scientific relevance. We were working with LRO continuously. We were working with JAXA and India and getting their data from their missions. But continuing forward, in the end, the signature for hydrogen was so compelling within Cabeus that we had to make that decision to go there at the expense of perhaps observability and other aspects. So I think it was the right decision, and time will tell exactly what we'll learn from it, but it was, I think, the right decision for sure. So that's where we are, and it was a 4-month cruise then after June 18th launch and impact on October 9th, and we've been buried in data ever since. So I'll leave it with that then, yeah.
Thanks, Tony. And as I understand it, you're going to go through a little bit of the data.
Yeah, once we hear, I think, Jen Diane talk, then I thought it'd be interesting to tell the final hour story actually looking at the data in a browser that one of our team members has built, essentially allows us to do that. Yeah.
Great. So stick around for that. Jen Heldmann, you were in charge of coordinating the telescopes that would be looking at the site and the Cabeus site that Tony's told us about. Can you tell us a little bit about that programming, that observing campaign that you set up?
Sure. So as Tony mentioned, part of the observability for LCROSS was to be from ground-based and space-based assets. we had the shepherding spacecraft, and then these observations are complementary to those 9 instruments on the shepherding spacecraft. So the approach that we took very early on was to try and engage the astronomy community, because it's not typical to observe the moon if you're an astronomer. You usually hate the moon, and it's this big bright thing obscuring the dark sky. Informing folks about it, going to the observatory directors first to let them know that this was coming down the pipe, so that when observing proposals came in, they weren't shocked and they understood where this was coming from. And then going to meetings and whatnot to drum up support. And so that worked quite well, and we ended up having on the order of 25 or so professional observatories, both on the ground and in space. The observatories were, the ground-based were basically in the western US and out through Hawaii, because that's where it was dark during impact, and that's where you could observe the LCROSS impacts. So that's celestial mechanics, can't do anything about that. But it was great because we strategically had observatories in these areas. And then of course Hawaii, where there's all the great professional observatories, which Diane will tell you about since she was actually out there on impact night. And then we had a few space-based assets. We had some Earth-observing satellites turned towards the moon, ICONOS and GUI and Earth-observing 1. HST, Hubble, was observing during the LCROSS impacts. I just want to say a quick note about Hubble. So just FYI, so for the Hubble observing, we were not pointing Hubble exactly at Cabeus at the impact point. It's too bright. Wasn't the best science that could be done there. So we weren't trying to take images of an impact plume coming up. What we were doing is we're pointing Hubble just off the limb of the moon and looking for any OH or exosphere species that would have been liberated from this impact. So we're off limb. We took before impact, we used STIS to take some baseline data. During the impact, we used the Wide Field Camera 3 in the OH band, and then several orbits after that, we took more STIS data and then STIS after that. So looking for some after effects, and that data analysis is still ongoing. And then LRO is in orbit around the moon. They're in a polar orbit, so in a great place to look. And I'll show you a little bit of the data LRO did observe. They've seen the crater itself and some evidence of the plume, etc. So there's good data from LRO, and since they're in orbit, they have multiple orbits where they can keep going back and looking, and so they're doing that as well. So just to get you...
They are right over the Cabeus region right now, I think, actually.
Perfect.
Yeah, doing follow-up observations, yeah.
So just to give you a little sense of where we are, so here's an image from New Mexico State and Marshall Space Flight Center, who were part of the observing campaign. This is the target crater Cabeus that Tony mentioned before, down near the south pole of the moon. Diane can tell you more about the challenges of pointing these very large telescopes at a very particular region on the moon, because she did probably the most work out of anybody figuring out how to do that and then sharing that information with the rest of the group. If you go to the next one. So here's one of the images from Diane showing the Cabeus crater. You can see there's this bright ridge before, and then you see the dark background, which is where we'd be looking for the plume itself. Go next. I'm just showing a little bit of sample data. This is from the Canada, France, Hawaii telescope. So they were also imaging out in Hawaii. And so this is the Cabeus region. You can see the brighter ridge and then the darker part behind that. And then you see the 2 black circles that are in there. And so what they were doing is they were taking spectra during and just after the impact. So you take a spectra at the darker circle on the bottom over the impact location, and then you take a calibration point above. So if there's any changes in the one below, you expect to see no changes in the one above because there's nothing happening there. So that was the methodology for that. Next. These are just some sample spectra from the MMT Observatory out in Arizona. I'm showing before and after, and the analysis is still ongoing. The basic story is that the folks that did spectra are analyzing their data. They see potential differences, and we're still working with them to figure out what these differences mean and if they're real or not. And that's basically the same story across the board. We're also still doing the analysis for the HST data. There are a couple other radio observations. The Swedish satellite Odin was observing from Earth orbit. They're looking at their spectra. SETI took observations from the ATA, so Jill and Samantha are still working on that data as well. And the approach we took with the observing campaign is for the professional astronomers that were a part of this, we actually folded them into the science team proper. So we treated them as an official part of the project, shared with them all the information that we had that would help them facilitate their observations. All of the work that we did with the site selection and the characterization and using the latest LRO data that we had, keeping them updated on the targets, the crater selection, all of that information we shared with the professional astronomers, because the whole philosophy for the observing campaign is to have as many telescopes pointed at the impact location to get as much information and learn as much as we can out of this entire experiment. And then there was also Brian Days here. Brian was organizing the amateur observing campaign. So I don't even know how many hundreds of people he had organized that were observing the impacts. So, and we also were soliciting those observations to send into NASA so we could look at them. So not only for science, but also for great public outreach and EPO activities. And on the night of impact, there were only 3 of us in the Science Operations Center. Tony, myself, and Kim Eniko-Smith, who was one of the payload leads. And so I was in direct communication with the astronomers who were out at the telescopes. So we had comm lines going out to them to keep them updated as to what was going on with the mission. You know, okay, we're this far out from separation. We have cleanly separated. We're going in. Here are the latest refined targets. Spacecraft payload is on. We're collecting data. You know, all of that information so that they could react in real time and have the most recent information. So I think that worked out pretty well. You know, countdown to when we're impacting and whatnot. So maybe we should let Diane talk about her observations.
Thanks, Jen. Yeah, Diane Wooden, you were out at Hawaii to observe the impact in your instrument PI on the or instrument co-I on the LCROSS mission. So maybe you could tell us about the preparations that you had to make before the impact.
Can we switch to my slides?
Sure can.
So my colleagues encouraged me to, we started talking about the challenges of this experiment, and I said, well, who's going to be the principal investigator on all the observing proposals? And they responded, well, why don't you do it, Diane? So basically, I assembled a team of colleagues who have worked together intensely on other projects, including deep impact. So, and I encouraged my colleague Elliott Young from Surrey to basically be the lead coordinator for these teams. So we had a very large collection of observers, which you see on the top part of the list, and collaborators from observatories in the lower part of the list, producing models and also working with telescopes. For instance, at Gemini Telescope, there were 15 people on the top of the mountain at the time of impact to get the telescope to do what we wanted it to do. So we were using only 1 out of 5 systems of the adaptive optics. We're using only tip-tilt in order to guide accurately on the moon. Because it's an extended source, we couldn't actually use all 5 components of the adaptive optics system. So next slide. Briefly, I'm just going to talk really quickly about the shape of the ejector curtain and how we chose our slits and the dust plume shape. And then later, if there's questions, we can talk about what the flux levels we expected to see versus what we're working on the data. Next slide. So here's a view of the top of Mauna Kea, and just a quick from left to right. The Gemini 8-meter telescope was used with the NIFS integral field unit, and in the middle is Canada, France, Hawaii, that was doing spectra with collaborator Christian Villet. And then the Subaru with the dotted line and the Keck 2 telescope next to it are looking for water vapor lines at very high resolution. And then the IRTF, the small silver dome, was looking for the dust evolution. So, and then I wanted to mention, very importantly, that the MMT with Faith Vilas was looking for water ice fundamental band, and there were assets on Maui looking in wide field visual spectropolarimetry and thermal, as well as other telescopes looking at the fast evolution of the plume. So as Tony will talk about, basically there's 3 parts of the plume. There's a bright impact flash, which we think might be 100 milliseconds in time, and the spectrometers on board the shepherding spacecraft were looking for that evolution. But what we, from the ground space observation, is possible, we would be seeing hot vapors, and I think they'll talk about the detection of sodium lines from McDonald Observatory and Kitt Peak Observatory, and that's very important because we know that sodium is typically in the exosphere of the moon, and to see that release from the regolith inside this permanently shadowed region is very interesting. And then the plume expansion, we expected to evolve between about 4 seconds and 2 to 4 minutes, and we do see that in the, Tony will talk about that. And then the residual thermal blanket was seen by the diviner. So these 3 phases that were discussed in our initial proposal actually are being assessed. Next slide, please. So we've been greatly helped out by many different people at UC Santa Cruz and University of Texas doing dynamical models, so to predict what we would see from the side. And basically, I explain it looks like a lampshade, upside down lampshade expanding sideways. And it's a very rapid expansion, so we expected to have about 2 minutes to get data. That's the fastest experiment I've ever done. There's no time for adjustment. If you wanted to count on adjustment, you might just push the wrong way. So we had to really point accurately. Next slide. So here's on the second image, the square is the field of view of the integral field unit spectrometer, which is 1,680 slits at the Gemini Observatory, looking in a similar wavelength region as the LCROSS shepherding spacecraft, but at a spectral resolving power of 5,000. And then the long slit is the IRTF slit. So you can see that we would catch the whole sideways evolution of the plume. Next slide. You click on the movie. So here's a wide field dust expansion and an estimate of the size of the Keck slit on that. And if you go to the next slide, this is actual slit viewing image taken 7 minutes before impact on the left side, and annular guider image on the right side, which we were using to verify the pointing. And that was a big part of my responsibility, was to tell astronomers how to offset accurately to the plume. So if you can tell in this annular guider image, right vertically above the arrow on the right-hand side is a crater, and that crater we called waypoint 5, and it's that crater from which we offset from. So we were trying to, as you can see the next couple slides, we were trying to snug the slit up to and parallel to the descending mountain ridge. That Cabeus is a deep crater, and the mountain in front is approximately 5 kilometers high, and we're impacting at about minus 3.8 kilometers below the average zero level of the lunar surface, lunar triaxial ellipsoid. And so basically this is the Goldstein model for the water vapor at 20 seconds on top of that. So there's a little tiny white dot. If you go to the next slide, I've zoomed into this, so and I flipped it over, so kind of the view that I flipped things from here on. So we actually impacted, the LOLA data was used to create wonderful shadow models, which matched the observations to a T, and were very helpful because the shadow was significantly different the night before impact. So we used the night before impact shadow models to confirm our pointing. And Elliott describes actually his work on the night of impact to be very minimal because we had practiced so well. And Elliott coordinated all 4 telescopes in a room on Mauna Kea mid-level facility. So we had 4 different screens from all 4 telescopes, Keck, Subaru, Gemini, and IRTF, and they were confirming that we were pointing at this location. So we pointed in the middle of what we called the candy cane there, and the impact was actually at the edge, so that's within the 1.75 radius uncertainty of the impacting position. And what I've overplotted there is the 21-second water vapor peanut. And the model actually takes into account that the sun horizon is not at impact, but is actually about a kilometer to kilometer and a half above impact. And you see there the slit position of the Keck slit and the slit width. That's the same as Subaru. The other instruments had slightly bigger fields of view, or they're positioning their slit parallel to the top of the mountain in order to get more of the sideways evolution of the dust. So the next slide.
So just a quick question there. The peanut is an actual model. We're not talking about the actual data.
That's right. It's a model. Right. Yep. So that's what we're going after, was that highest density part of the ejecta water vapor with this instrument. So I just wanted to show you sort of some movies. If you click on the right-hand image, this is a movie of the grain column density we expected to see pass through the slit, approximately 5 times 10 to the 5 particles per meter squared. The next slide shows the water column that we expected to see. You know, a lot of the water you see there kind of going down onto the surface and then hopping back off the surface in a little bit because the surface is so cold. There was some sort of there was definitely an interesting aspect of the model. And the next slide shows the ratio. So this was one of our concerns, was whether to try to clip some initial part of the data acquisition out. Can you go back and redo that one? So the thing is, this is the water column to dust column, and basically where the slit position is this ratio is about the same. We were at first worried that it would be saturated by the dust continuum and that we'd have to take some kind of fancy sequence where we saved 5 seconds of data right after the impact and didn't co-add that with the rest. But it turned out that these models were critical. We received these models basically Friday before the impact following Thursday. So we really appreciate the hard work of our collaborators at the University of Texas. So that's a description of the experiment. All 4 telescopes pointed exactly where we wanted to, and our data was started 20 seconds before impact. We started a sequence 4 minutes before impact, but the frames that had impact started 20 seconds before impact, and then the second impact was caught at the 3rd frame after that. So we have spectral resolution of 27,000 data, and we are in the process of analyzing this. So I just say that the experiment went off perfectly well, partly from the dedication of more than tens of people per telescope. And once the telescopes accepted the observing proposals, they took it on in a tremendous amount of effort and technical time to make sure that these experiments happened with success, and we got excellent data.
All right. So what I'm going to talk about is the shepherding spacecraft data and the observations. And as I mentioned early on, it had a particularly unique view as it flew directly at the impact and through the plume and remnant plume, and then impacted itself. As Diane showed that first image, or actually the cartoon from our proposal, which showed the flash, the curtain, and the crater. And that was part of our observation philosophy. What we built into this was as much robustness as possible because of the uncertainties, total uncertainties associated with crashing an empty rocket into the moon, into a dark hole you can't see into. So what we did was we want to emphasize, one, the flash. The flash produces luminescence for you, so you actually have a self-luminescent source. So even if no ejecta moved anywhere, you had some information from there. So we had built instruments specific and ran instruments very specific to that event. And then the curtain, we changed the settings and had instruments specific to the curtain, trying to observe that and measure that, and then the crater as well. And so we covered wavelength ranges from the ultraviolet, about 260 nanometers, all the way out to about 660 nanometers. And then in the near infrared, we had cameras covering about 0.9 to 1.7 microns. And then we picked up spectroscopically again in the near infrared from about 1.25 out to about 2.4 microns, 2.3 microns in the near infrared. And then we had thermal cameras out past 7 microns. So we try to cover a gamut because we really didn't want to miss anything that could potentially be there. And so it was an interesting mix of measurements. A lot of them are corroborative, meaning if we see something there and here, they should agree at least to some sense. And so you're not relying on just a single measurement. And that was, I think, is really playing out to our benefit right now. So what I have up here on the computer is a tool that our software lead, Mark Shirley, built, customized for this project. We call it the data browser. And this is an interesting mission. LCROSS is, unlike most missions, it's real time. We never repeated anything twice. We did a swing by of the moon very early on. We did a lot of calibrations there, but we never saw the moon again up close until impact. We had a variety of Earth calibrations, which are actually really interesting data sets, looking at the Earth from up to 550,000 kilometers away with all of our instruments. But we never looked at the Earth at the same phase, the same distance and whatnot, which is interesting in itself, but in terms of a calibration, it has its own problems. And then so this tool was built to actually display linearly in time what took place. And so you can actually walk through the data and see how things are changing and hunt for things. So actually the morning after our Saturday morning, after the impact day, the science team got together, a smaller subset, about 7 of us, and walked through this starting at about 9 or so a.m. And I finally had to break it up at around 1 or so, even though people didn't want to break it up, but my wife was calling and she said, get home. The kids are ready to go to the pumpkin patch. But it was that Saturday morning, Jen was there, Diane wasn't there, you were still in Hawaii, that we realized we had an incredible wealth of data, that it was actually much, much richer than we ever anticipated and hoped for. And we will be looking at this for, I think, years actually to come. We've been digging into just individual instruments. The science, I've distributed the data to the science team members, the internal science team members. We've got teams who are kind of focused on reconstruction of the impact, near-infrared spectroscopy, ultraviolet visible emission spectroscopy, and image analysis. And we're still not able to, you know, we're still leaving data on the table that, with no one to look at it just yet, because the other data is so rich. What you see here, all these black lines at the top, this is time across the top in minutes. And what we did was we turned the instruments on about 1 hour prior to impact, 55 minutes prior to impact actually. And we go through a warm-up period. And that's to allow all the instruments to come into their steady state. Some of them have calibration trends that we knew about from operating them in space that we wanted to get out into the, you know, the level calibration zone, the calibration area of the instrument we understood. And we actually checked camera settings and things like that. It was very real time. It was quite hectic because it was real time. So you had about 55 minutes of, yeah, everything looks good, and then 4 minutes of, and that's what we had. So all these little black ticks here are measurements. And along the side up here are the visible camera. We had a 3-color visible context camera, 2 near-infrared cameras with different wavelength band passes, 2 thermal cameras, 2 near-infrared spectrometers. One NSP1 was nadir looking down at the impact. NSP2 was looking to the sun. And so it measured the sun all the way down to impact, so we could look for occultation of the sunlight by materials and vapors. And then we had an ultraviolet visible spectrometer looking nadir as well, and that was the ultraviolet through visible wavelengths with fairly good wavelength resolution. And then we had a total luminescence photometer, which the ticks don't show up in this particular version of the browser. It was an instrument built that had 1,000 samples a second to measure changes in the luminescence, to look for the flash of the impact in the curtain and whatnot following the impact. So we can walk through this, and each of these ticks indicates essentially a sample from one of those instruments. And you can see across the top here, all this here, up to here is essentially pre-impact preparation calibration measurements. And right at this point, you see we turn off the visible camera, we turn off one of the near-infrared cameras, we change the rate on a near-infrared camera, and we go into what we actually change the mode of operation of one of our near-infrared spectrometers. And this is a flash period. We knew the impact was going to occur right about here. We prepare ourselves by getting our instruments into a particular flash mode for observing the flash. And then we come out of that for the curtain mode. And the curtain mode runs right up to here, and you can see we turn off 2 of our cameras, we change our cadence on some of our other instruments. This period right through here is the crater period. So those 3 periods that Diane showed in that graph are represented here in terms of flash, curtain, and crater. And so we really did build the entire operation around that. So I can click anywhere on here, and it's where this blue line is over here on the left. It will bring up the closest data product for that time tick. And what you see down here is I can make this a little bit larger, is a visible color image of the moon. We're about 8,000 kilometers away at this point. Another thing that you can see here is this black line here. This is this is an important point actually to understand the total operations and the madness we had to deal with. Is we were bent pipe, meaning we streamed real-time all the data. You know, obviously no store and forward when you're going to be 6 feet under at the end of your mission. So we had to live within a fixed bandwidth of 1 megabit per second. And we had compression, very aggressive wavelet compression on the images, some of the images. But the scene constantly changes. As you get closer and closer, the complexity and everything else, the compression changes. So we had to manage real-time, maximize the data rate, yet manage the bandwidth so you didn't start dropping images. And we had a prioritization set up on the data. First thing you drop is your visible images. They're pretty, but See ya. And then the near-infrared images, we lose those. Hold on to the mid-infrared, and at all costs hold on to the spectra, because that's actually where most of the science is. So I don't know if any of you are following the flight loop, but Kim Eniko Smith, her nickname now, at least for me, is Kim November Smith. And that was Kim calling to flight to change one of the OPR settings, one of the exposure settings on a near-infrared camera. Her and I in the SOC would discuss, we're getting close to dropping. We could see the drops of the visible camera. Okay, the rate's increased. Let's decrease the rate on a thermal camera. And so you'll see we actually managed this real time all the way through here in preparation for the impact. So it was not a sit back and watch. It was really a very active, engaged mission all the way through to the very last seconds of the impact. We changed the OPR setting, one of the gain settings on the near-infrared camera, and we got it in there in time. The flight team was awesome, and it revealed, honestly, I think some of the most spectacular data, unexpected data that we've seen so far. So if I reduce the size of this image now, and go back over here and find the little minus sign here, there it is. Down below here we have all the cameras. I just need a bigger monitor. You have the near-infrared camera here, near-infrared 2, and they're showing as white because right in the beginning we're still in setup. We're actually just setup. And then the mid-infrared cameras, and there's a false color of a mid-infrared there, and there's a mid-infrared normally there. And then down the bottom here you have the spectrometers. This one here on the left is the ultraviolet visible spectrometer. And just so you know, this is all uncalibrated, so you can't take this and deduce anything, conclude anything from it, because there's no calibrations applied to this data set. And I wouldn't show you the calibrated data, that would be bad. And so this is the ultraviolet visible spectrometer. I can tell you this is in the 300 nanometer, 350 nanometer range through here, all the way up to about 600 nanometers, or 660 nanometers here. This is our downward-looking near-infrared spectrometer. And the shape looks like the solar spectrum. It's not. That's purely an instrument response function. So don't read anything into these shapes. And here's the side viewing solar spectrometer. So this is, again, a near-infrared spectrometer. It's an identical instrument, but looks to the sun. And you can see, in terms of counts, we have about 25,000 counts here. So good signal to noise, very good signal to noise. Here, we have nearly 1 million counts. And that's why we look to the sun, is we had what I call stupid signal to noise here. It was just incredible. It's hard to see the noise in the signal. So, and we maintain that all the way down to impact. So what we can do now is kind of zoom in here. So if we go back to the image of the moon, we can kind of, if I click to here, now you can see some of our infrared imagers have come on and we're a little bit closer. And we can just kind of see the moon as I click, come in and in closer. If we click on the MIR, that's mid-infrared. Let's go over to the near-infrared here. 2, there we go. So pretty picture in the near-infrared of the moon as we come in. You can see that green X is awfully close to our impact spot, but it's not. Here's Cabeus, where we're headed in towards, and you can just watch ourselves come in. And this is basically what we did stream out to the web. Of course, the spectrometer data is changing all the time as we come in. The field of view of this image here is about 24 by 24 degrees. The field of view of our spectrometers were 1 degree, so a much smaller circle within here. And that was really key because actually a little bit prior to impact, our field of view only see the shadowed bottom of the crater. And so again, this was one of the very strong, unique aspects of our spacecraft that no one else could reproduce. Was as we came in, we only saw black crater floor with our spectrometer, so anything coming up out of there was basically from the impact event itself. We got scatter light from around us, of course, but that's fairly easily subtracted off. We didn't have any background signature into our instruments. So as you can see, we're moving in, and the scene changes more and more closely here. We're probably about 700 or so kilometers above the surface. Here you see the Cabeus crater. Here's Cabeus A. That was our first target. And the issue with Cabeus A, while it had the best observability, and that's why we first picked it, in the end, the consensus was very weak regarding its the concentrations of hydrogen seen there. there was lots of uncertainty in the data sets, and there still is, for these lower latitude targets. This is fairly low latitude, about 81 degrees south. And the actual area that seemed indicative of higher concentrations of hydrogen were in sunlight. As you might have heard from the land presentation, they saw some very strange things. That was in, a lot of people didn't know how to interpret that. We did analysis with the thermal gradients, thermal models. We pounded this. It's amazing. I was working with all the LRO PIs of their instruments at 2 or 3 a.m. for weeks or so up to this. And what was great too was we were supposed to make the decision a month ago. I mean, that was Cabeus A. But we didn't. We were so on target for the Cabeus region, we didn't have to do any maneuvers, which gave us more time to really rethink and rethink. That plus the fact that we did a payload operation on our spacecraft and the payload checked out in perfect health. If it didn't, then we would have probably stayed with Cabeus A. Meant that Cabeus was the most viable target, the most relevant target. All the data from all the missions, previous and current, said Cabeus had lots of hydrogen. So we couldn't ignore that, and we had to go there. Our impact site was right in here. Again, allowing for, there's a little valley here that allowed sunlight to come in, illuminate it at fairly low altitude, about a kilometer, 1.1 or so kilometers above the surface, maybe. And then we were trying to get it as far this way, down towards the page as possible, so we could look past, for the ground observers, past the hill here. So as we go in, we get these beautiful infrared images too that are just spectacular. Go over here and pull up, if I can. This is MIR2, which has a slight defocus, but is actually more sensitive. These temperatures here are about 40 or 50 degrees centigrade. The purple we saturate down at about minus 60 degrees centigrade. The actual temperature where we impact has been measured by Diviner to be about minus 220, 240 degrees centigrade, so about 40 Kelvin or so. So about as cold as Pluto. You can trap a lot of stuff at that temperature. So we flew in then some more, and we're getting close here. We'll go back. There's the mid-infrared 1. It's a little bit more clear. We're getting real close. Where we impacted is right here in this area. And then you can see, if I come back to this presentation up here now, if I drop this down and we look at the data, I can zoom in on this. And we can expand. You can see all the data. All those ticks are images. All these are spectra. So we got a lot of data. We got about 2.5 gigabytes of data prior to impact. And then we can zoom in here, and this is the flash part of the impact. Right through here, we change our cadence. We've determined that the impact flash actually happened right about here. And we can go to the cameras, and some of those have been posted online. Let's see if I can actually find the image here, real time, where we see the thermal impact flash. Might be hard to see on your guys' screen. Actually, let's go to MIR2 here, if I can. Again, homegrown product. It works about as well as Microsoft. So, I didn't say that, did I? Yeah.
We've got it in the PowerPoint. Yeah,
you'll show them the PowerPoint. It's hard to find it real time. The impact occurred in there. What's fun though is, we looked at some of the spectra here. That's a cosmic ray. Ignore that. But if we there's lots of things here, properties, go to VSP. It's got a variety of, we go to this high integration time. We go to a 2-second integration time with our ultraviolet visible spectrometer during the impact, because we wanted, again, there was uncertainty to about a second of when it would impact, so we wanted to make sure we caught it, plus have a long integration time. And if we scroll over here, actually I was on the wrong side of the flash. Right here, you can see this is prior to impact, pretty smooth curve. Right after impact, there's sodium right there. That's a very strong sodium emission line. We've actually detected at least 3 sodium emission lines, corroborating everything. What we can get is the temperature from that. We see lots and lots and lots and lots of other emission lines through there. So we saw much, much more than sodium in the flash data alone. which is really exciting. And we've got a couple scans worth of that. There's another one, very strong lines coming in, and then they go away as the hot vapor plume, as the molecules relax and atomic species relax, although we actually have monitored emission lines extending all the way through this period now. So very exciting data set there. And then the near-infrared spectra, again here, it's just looking into blackness. We did post a light curve, total radiance curve for these on the web that showed that both spectrometers detected the flash and the roll-off of the curtain very nicely, so we got very good signal to noise. So to wrap up this real quick, we just keep flying in closer and closer. There's monitoring, all this is data. We've got this huge amount of data, and honestly, we've been blown away. And that was a quote that was attributed to me, and I keep saying it, but it's really true. We were kind of looking at this going, wow, there's so much in this. Where do we begin? Then we go into crater mode. And what's fun about crater mode is we did an experiment. One, the visible camera picture here stops. It takes a lot of bandwidth, so we turn it off. After all, we're going into a black hole. But what we did was, and we turned off near-infrared 1. Near-infrared 1 has a water vapor band filter on it, so it has lower throughput. But we did go to a near-infrared 2. Now near-infrared 2, right here, it's totally saturated, static. And we set that high because we knew we were going into a black hole. And what it's seeing right now is the bright rim still to either side. And it's bleeding. It's saturating and bleeding across the detector. Kim and I were monitoring this, and we were saying, and this is when she was going November, November, November. I was trying to set it to a low, this was at one particular gain setting. We concluded within the time of 10 seconds. That's the time you have to conclude something here. We wanted to go to a different setting. And that's why we looked at the Earth and the Moon and so many different phases and whatnot, is to understand these cameras and the spectrometers so you can make real-time decisions. So we set the gain to something, and she said, I remember Kim saying, do we need to go lower? It's still saturated. And I'm like, no, just wait another second. And then it started to appear, and I'll go this. Nope, this is the floor of Cabeus. We actually begin to see, for the first time, before anybody, that I sure can. So we come in, and what you'll see here is from one image to the next, there. So this area here is still saturated, and I'm sorry, it doesn't. Here, I can move this up a little bit. But then now I've done it. It's still saturated through here. Of course, it's bleeding, but now you can start to see some images. And if we get in closer, we finally get below the rims of Cabeus, and everything starts to come in as we fly in. And there we are. We're about, as you can see at the timeline here, the actual data cutoff was right there. Last transmitted image right there. That's about 1 second prior to impact. So we were receiving telemetry approximately 1 second prior to our impact and got data, including spectra, and we actually have signal in the spectra from the spectrometers all the way down into impact. So they were seeing scattered light onto the floor. What you see here is a variety of craters, some very interesting things, and I don't want to dwell on this too long, otherwise my co-eyes will get angry at me. But what I will show as we come in is this little crater right here where the arrow is a Centaur crater. And so we are able to image our crater. We saw this also in the thermal infrared. You see this red dot down here in the corner? Right there? That's it in the thermal. And as was mentioned, diviner's seen it as well. You notice this entire area is kind of glowing. A little bit of green. Diviner seeing some interesting things here as well. We think really what that is part of the, it's offset because of the crumpled Centaur to the one side. And actually, in more thorough analysis of this near-infrared images, we think we actually can see there, right there, that's actually the centaur crumpled to one side, the remnants of the impact to one side of the crater. And this is the entire crater region here. So we measured it, it's about 38, in this near-infrared image, about 38 meters or so across, and that's the final image, and you can see it right there, just out of field of view as we went in. So our final image resolution in these images is about 2 meters per pixel, and it's a very interesting data set. There's lots of interesting things in it once you start seeing it, when you should start looking at it. So with that, I'll leave it, and you can see over actually down here some of the visible spectrometer data. It's noisy, but we actually still have quite a bit of signal. Our noise floor is about right down here, 2300, but through the visible here, we're seeing enough scattered light to actually do some spectroscopy of the floor of Cabeus without the ejecta plume even.
So Tony just showed you the wealth of data, and this is what we've been doing every day since impact, and it's going through this fantastic data set. So we just have some images and whatnot that we've pulled together just as a sampling of the type of data that we have in more detail. So we've got zoomed in shots of from the mid-IRs and the near-IRs with the impact site. As Tony mentioned, we have the spectra where you can actually see the counts, radiance going up in both the vis and the near-IR spectrometers, so we can actually tell. You can see the flash, you can see the curtain, and as that pans through. We also have, in the visible camera, we've detected the plume, and so we posted that online as well. So we have multiple images of the plume as we're going in. And so we're working the data sets now. As you can see, there's a lot, and working on writing the science papers, because before any big announcements are made, things need to go through peer review and go through the scientific process before we come out and say, what's there? So maybe we'll just
We saw the moon.
We saw the moon, for sure.
We detected the moon.
You can keep going. This is just from the viz going in. You've already seen that from Tony. These are some of the near-IRs going in. Mid-IRs going in towards Cabeus. Here's one of the images. This is from the visible camera. So what we've done here is co-added a few images. You can see it in individual images too, and you can see circled in there is the actual plume itself. You can see it spans quite a few pixels, and we know how far away we are, and we know how good our cameras are, so we know how big things are. Next. So this is just counting up all the counts in brightness from the VSP, from the visible spectrometer. So you can see we start going in. Oh, the blip. So you can see us coming in. You're getting a lot of flux as we're coming in. You're seeing parts of the moon, but then we get into the dark region, like Tony said. Right. You see that drop? So now we're just looking at the permanently shadowed regions. And then you see the blip from the impact. So we see that our counts go up. You saw the tremendous number of individual spectra that we have that have individual lines in it. And we're going through all of those now. And then at the end is nothing to pay attention to. If you go to the next.
More of a processing artifact than an instrument artifact.
And this is the plot that Tony mentioned before, showing the UV visible spectrometer and near-infrared spectrometer. You can see the levels that we're at before impact. You can see the point of flash. You see the blue line, which is the UV vis, shoots right up, and then you can see as we go through the ejecta plume through the curtain phase as things settle back down. We're also seeing a similar trend in the near-IR spectrometers, so there's a lot of information in the near-IR as well. And then you see we drop back down. And Tony showed you this is just a cropped in area where we've seen the Centaur crater in the mid-infrared cameras. So we're on the order of 4 meters per pixel resolution now. So we're getting very good resolution in these permanently shadowed regions that have never been seen before. Next. Here's the Centaur crater in the near-infrared. Here we're at about 2 meters per pixel. So these are the 0.9 to 1.7 micron images. Go to next. So here is the mid-infrared. So this is, we have a temperature calibration, as Tony mentioned, so this image is temperature calibrated. So your whites are on the order of 35, reds are about plus 18 C, dark blues on the order of minus 45, and then below minus 50, minus 60, we're not sensitive anymore because we're at these extremely cold temperatures. So you can see there's the, where you see the impact location where the yellow arrow is. So you can get temperatures out of that, which we're doing, and you can get temperature profiles as a function of time, which we're also doing. Next. And here's just a time series from the mid-infrared. So if you start over on the left, here's the mid-IR camera 2 seconds before impact. That scene should be starting to look familiar now. There's nothing there before impact, and the next image over is just that same frame, but stretched as far as we could stretch it to make sure that really there's nothing there. And then we go at the time of impact at t is 0. Then you see the remnant up there with the red arrow. And then as you follow this as a function of time, 2, 4, 6 seconds, and continually on out, we can watch the thermal evolution of that location. And so we're doing that now as well. And we have temperature calibration, so we can actually do some thermal analysis. And then here's, again, this is very similar with the mid-IRs, and then doing this time series out. And here, these ones are just white is hot and black is cold, in some enhanced contrast on the other side with some image processing that we're doing. And then this is just a shot from LRO. So this is the diviner data that Tony mentioned. These are thermal channels. If you look at the top panel, they don't see anything before impact. And then after impact, there's a little dot sort of in the middle bottom part. Yeah. My assistant will point out the crater. So this is from LRO, yeah. And since they're in polar orbit around the moon, they're doing follow-ups, and they're there at the moment. So that's just an idea of a closer-in view of some of the tremendous amount of data that we have and that we're actively working on.
So, thanks, Jen. So, Diane, you got some results from Hawaii that you're able to show us.
This is a good slide to do on the first slide, which is just to say that we're working very hard on the data. And I'm a science team member on LCROSS, specializing in near-infrared spectrometers. So I worked for a week on the Mauna Kea data, and I came back and said, I think we see some inflections in the spectra at this location, slightly down the mountain. And Tony and Jen said, well, that's actually where the sun horizon of the ejecta plume kind of intersects the mountain. So I'm now concentrating on near-infrared spectrometer data, and with that information, go back to the high-resolution, low-resolution data and work again. So I am just to say that all the data that was acquired by all the telescopes were acquired with extreme excellence and attentiveness to detail, and we're working on data.
If you'll join me in thanking our speakers, just clearly some fantastic data there, Tony. And now I'll open the floor for questions.
Like Tony's glass is empty and mine is full, so I don't know what that means.
No comment.
I was curious, what time of the lunar day was it? What time of the lunar day was it when the impact occurred? Was it morning or noon or afternoon?
With respect to
time of impact on the moon.
yeah, what time? I'm trying to understand with respect to the spacecraft. Yeah, whereas the sun was, it was I guess not quite 3/4 full. It was the phase, if that's what you're asking.
No.
The moon was 3/4 phase.
Okay, so that would mean, well, I mean, was the sun directly overhead? Was the sun?
No, the sun is in the ecliptic plane. We're at the pole, so the sun was about. It was a favorable libration for view of Earth, but the sun was about 1 degree and a quarter above the horizon or so.
Oh, okay.
But the bottom of a crater never sees the sun. So
No, it does not.
Right.
I guess that tells you.
Yes, these are. We had impacted into an area of the crater that is permanently or near permanently shadowed, meaning over the last couple billion years it hasn't seen sunlight.
I read some bad press after the impacts about the plume not being as visible as predicted. So what was the magnitude of the plume, and why was it not as bright as predicted?
It was in the lower end of our prediction range, and we had a variety of Monte Carlo simulations, and the actual range of possibilities spanned about an order of magnitude. And so, you know, we tried to work within that and design a mission, which is kind of hard. Engineers don't like you saying, well, I don't know the answer to an order of magnitude. So we designed towards the lower end. It was fainter than what we were anticipating. The flash was very interesting. The flash looks like it was completely suppressed. But the ejecta curtain was self-luminescent, but the initial flash was greatly suppressed. The ejecta did get to at least 1.5 kilometers because that's where the sunlight hits the visible camera, ejecta. What's interesting is, again, it's a hollow spacecraft, mostly aluminum, impacting, and it's pretty clear to us right now that one of the models was a pancake model, that this thing would pancake, and if it hit into relatively loose, not very well consolidated material that allowed for a lot of compaction, we would have a lower angle of incident of ejecta, and that would result in much more diffuse plume, or ejecta cloud. That said, what did also occur was a very high angle, it appears, this is all really preliminary, high angle ejecta plume that came up very quickly, about 500 meters per second, very short after impact. And that's what we saw in our initial luminescence scans, our initial observations. It's also what LAMP then, the Lyman alpha mapping spectrometer on LRO, detected a signal as high as 15 kilometers above the crater. So material got up there. It was a different, somewhat different variety than what we were expecting. A number of experiments Pete Schultz did at Ames in the vertical gun, he just got to hollow shots about 6 months prior to impact, and he was seeing results consistent with this idea, and that's kind of what we're basing a lot of this interpretation on, is that a slow impact, 2.5 kilometers per second, with a low density object into a low density material that allows for a lot of compaction will result in a cavitation and a splash. It's like the milk drop, but it's a different process. You get something come straight up the middle, and then you have a much more lower angle ejecta coming out to the sides. So that could explain why the ejected cloud isn't more traditional, I guess.
What was the brightness magnitude?
Our fluxes, our total radiance, and our spectrometer measurements were below what we are anticipating. But again, for anybody, the total ejecta into sunlight was less than the nominal model predicted, but it could be explained based on these studies that Pete has done, and some of the observations are really indicating that it behaved differently than a traditional impact. That's for sure. Yeah.
So I understand that you have a lot of data to go through, but do you have any idea of the earliest time that you'd be able to publish your conclusions?
I've set a goal for the team to have results to present at LEAG on November 17th. We are trying to organize a team meeting at Ames the week of November 2nd. Paper writing has begun, and we hope to actually get a formal announcements, more formal, I guess, by AGU. Yeah. We'll see. That's why I proposed to the team. I didn't say that's what we're going to do. Yeah. You got to raise your hand higher.
Oh, hello. You know, I'm actually not a scientist. I don't know how many people in this room are. But one thing I was really impressed, and that sort of led me to come to this presentation, was, I guess, the impressive amount of cultural kinds of capital, or cultural signification of this experiment. I think that there was a lot of really interesting ways that people who aren't scientists became very involved and interested in what you were studying. And I think that today's presentation was very informative in that, you know, you've sort of shown that you've been able to successfully pick a target, you know, to measure it, to model it. And I guess given the fact that your results are going to be somewhat in the future in November, I guess I was wondering, what are the questions that you're subjecting to this data?
What was your question again?
What are the major questions that you're subjecting to this tremendous amount of data that?
The principle, well, if I understand your question, and you're absolutely right. It's been an adventure, to say the least, from day one, from a cultural aspect, a scientific aspect, a professional aspect, and I think we've all learned. The lessons learned are, the list is as rich or richer than the data, honestly. But our principal goal right now to the exploration directorate is to answer the question whether or not the hydrogen is in the form of water or not. And then if it is, an estimate of the concentration. That is supposed to be a steering mechanism for future missions, robotic or human or whatever. So that is what I directed the team to emphasize on. One, to understand the cratering process so we can interpret the results. That goes hand in hand. We can't interpret what we're seeing spectroscopically without understanding the event. And it's one thing that we've all noticed, and Diane and Jen can comment on this as they've been looking at the data really closely, is this was a very dynamic event. It was things were changing over courses of tens of seconds, you know. So understanding really the process, what happened, is in parallel as important as understanding then spectroscopically, do we see water or not? Those are the things we're really emphasizing right now. And then everything else is going to have to come after that. Hopefully that answers your question. And Sandy had a question.
Yeah.
My question is, did the Centaur hit normal to the surface? And how much of the Centaur was pulverized by the impact? Can you tell anything about that?
We don't know yet. What we did do separation monitoring with our cameras, and we got a very nominal tip-off, so it looked good. We saw there was some rotation, so it was tumbling through space after our separation, and that was to be expected. No separation system's perfect. I mean, the separation system, the longest they had ever used it was like an hour and a half after launch, let alone 120 days after launch. So I'm glad it detached, let alone. But otherwise, it would. It is now, because it is now. Now we can laugh about it. But we did get a lot of. There were a number of observations from the ground of the Centaur going in, and there are some hopes to do some photometric studies of these.
Yeah, I have that video, which I forgot to show, which is from one of the ground base from the Magdalena Ridge Observatory, where they tracked the Centaur after separation. And if Adrian can pull it up real quick, you can see it's brighter, and then it fades and brighter and fades. So we were just talking with the NAV folks yesterday, and they're very interested in all the ground-based observations. So yeah, so see the stars streaking by, and then they're tracking the Centaur quite well in the center, and you can see that it gets fainter and then it gets brighter. So if there's some sort of rotation in there.
Yeah, we expect this tumbling. From our tip-off, we could see it actually in our cameras fade away and with a slight rate. And you'd expect it to tumble. The period of time from separation to impact was 9 hours, so you had a lot of time there to build, let this thing tumble. Also, there are parts of the Centaur that may degas that haven't seen much sun, and that would impart a little bit of a moment to it as well. We actually had 3 activities during mission where we turned the cold side of the Centaur that never saw sun to the sun to bake off material. The first time we did it was back in early July or mid-July, and we knew, I mean, this was always planned, we knew that there would be ice on the back of that, because it's a great big thermos in Florida. You know, you're going to have ice there. And so we turned it, and all of a sudden, yeah, our star tracker shut down. Said, I'm seeing all kinds of stuff. These aren't stars. I'm shutting down. And our navigation team, which just blows my mind how they do this stuff, but they reported from Doppler 3.5 centimeter per second delta V push on the entire Centaur. And so we said, okay, let's do, because we were worried about targeting and contamination. So we did it until we didn't see any effect anymore, basically. And that's, but there was still this possibility that some part might have degassed, which would induce more of a tumble.
Is there any residual fuel in the Centaur?
There was probably, there was no hydrazine. We vented all that. We were able to maintain the valves open on the liquid oxygen. Essentially, you can hold the solenoids open so long before they overheat in space. Again, not meant to do this. You know, Centaurs weren't meant to do this kind of stuff. And then also what happens is then we drain the tank so low that there's just bleed lines that take longer to go from one tank to the fill and drain valves. The estimates based on, the good news was we saw almost no no pushes from the fill drain valves, which we were worried about. Our last estimate was probably a couple kilograms of hydrogen, H2, and maybe 20 to 30 kilograms of O2 left in the tanks. Out of 2,300 kilograms, 2,350 kilograms. So.
Because there was speculation on the deep impact, I think, that the residual hydrazine was what they saw.
Yeah, we dumped a lot. We dumped all of our hydrazine in that about 45 minutes after launch or so. And then left those were pinned open. So that's dry. Now, so yeah, to answer your question, we don't know, but hopefully we'll find out.
Okay, if there are no further questions, I'm just going to stick in the last question.
That's so cool.
Tony, and for the whole team, if you were to do an LCROSS 2, what would you change in 30 seconds or less? And this is for everybody.
Boy, what would I change? Top of the list, I haven't.
Given another, in NASA's generosity, if you were given another $80 million.
Another $80 million. And well, I think we did a lot of things right on LCROSS. I think, you know, hitting with something that is a Centaur the Centaur had its benefits and its weaknesses. It pancaked, low density, so that really caused a lot of ejected not to get very high. If you went with something more like deep impact, higher velocity, higher density object, you get a lot more ejecta flying upward. That would be nice, but again, we wouldn't have been able to fit that into our mass budget. In terms of operations of the instruments, you know, the instrument selection I think was as good as we could have hoped for, honestly. It would have been nice to have a 3-micron fundamental, but that was one of those pushes of capability versus availability. So I think what I would change is probably a longer cruise with more time to characterize the target. We luckily had just enough, but I think it was just barely enough.
Jen, what about you? What would you
I'll just take the easy answer and say another target. Whether it's Cabeus A, whether it's Shoemaker, whether it's the North Pole, because now we have
one data point.
One data point, exactly. It's hard to draw a line.
Okay.
No, it's very easy to draw. Unconstrained, any line.
And Diane, what would you change if you were given LCROSS 2?
I would like a longer cruise so that we could have impacted at the South Pole high summer, so we had a better angle from Earth view, with the sun view being the sun angle being the same. And I would have wished for the blessings of the Chandrayaan spacecraft to still be working so that we could have had the M-cubed 3-micron data to come.
Chandrayaan again and wait a little bit longer. I mean, it's simple. Yeah.
So we were just very, very sad that it
sad.
suddenly stopped communicating with Earth in early September, just after Labor Day or so. So.
Yeah, because they were on board in the observation campaign to observe the impacts with M-cubed.
Which was visible through 3 microns.
3 microns, just up to 3.
Just up to 3 micron spectrometer.
Well, I guess you can't have absolutely everything, but it looks like you guys have got a fantastic amount of stuff to work through. So,
no one can blame you.